afternoon, everyone. So welcome back to our discussion on single cycle processor. We were almost done, but not quite. So we were looking at the design of the decoder, and we had seen that the decoder is divided into three parts: PC logic, main decoder, ALU decoder. This again is just for administrative convenience. It doesn't have to be. Like for example, when you implement it, it's very okay to implement it as one single module. Okay, it doesn't have to be split into the three separate modules. But here, I'm just following the textbook in which they did it just so that there is some modularity. Yeah, that's all. Functionally, it's not essential to split it into three blocks at all. And we had seen this part. I'm not going to bother explaining again. So we had seen the main decoder, ALU decoder, and this is where we were before we stopped the last session. So I had mentioned that PC logic is the part which generates PCS, and PCS goes to the data path not directly, but conditioned by conditional logic, right? So PCS is asserted when your program counter value is supposed to change abruptly. For usual instructions, it will increment by 4, right? But when it is supposed to change abruptly, we have to assert PC SRC so that the so-called result, which is the branch target address that is computed by the arithmetic and logic unit, will go into PC instead of PC plus 4. And to generate PC SRC, we have to generate PCS and condition it through the conditional unit. And what are the situations in which PC is supposed to change abruptly? When the instruction is a branch instruction, that is when opcode is 10, you have a branch. The other situation is when you have an instruction which writes to R15, which has R15 as its destination. For example, something like R15, whatever. So this changes R15 abruptly rather than incrementing it by 4 as is usually the case. So we check whether the destination register is R15 or 15, and we also check whether it is an instruction which is supposed to write to some register. And this guard was required to make sure that which instruction does not change PCs previously. This write W is a guard against store instruction. Because for a store instruction, if it is something like say str R15, something, it's not something which changes PC abruptly. Because for store instruction, RD is a source, data source, not a destination. Okay, so this instruction should not cause PC to be changed abruptly. And the guard to prevent str from changing PC is regW. str instruction will have regW is equal to 0 because str does not change a register, right? So this will be 0, and that will ensure that even if RD is equal to 15, it's not going to assert PCS. And PCS becomes PC SRC if the instruction is supposed to be executed. Remember, every instruction can be conditionally executed, right? And if the condition is true, PCS is PC SRC. If the condition is not true, PC SRC is not asserted, so PCS is effectively cancelled out, and PC SRC will become 0, which will cause your PC to increment in the normal manner. And here you can see there are these 4 control signals which are not given directly to data path. In fact, flag W doesn't go to data path at all. It's just to write flag registers, and here according to our design, flag registers are considered to be a part of your conditional unit, which is in fact a part of your control unit. So it doesn't go into data path because the conditions are stored inside the conditional unit. And the 3 signals that eventually go to data path are PC SRC, when PC is supposed to be changed abruptly, reg write for most instructions which have a destination register, or for all instructions which are supposed to change something in the register file. And this is to write to the memory, which is for str. So this is to change PC value. This is to write to a register file, write to a register in the register file. This is to write to memory. So these are the three things which have the ability to change the state of the processor, right? And those three signals are conditioned. You don't have to block other signals because if these three are zero, whatever happens in your processor is not your concern at all, because eventually nothing changes, right? Other than PC getting incremented to PC plus 4. That's the idea. Okay, now this diagram can be a bit confusing because here it looks like there are two flip-flops, but if you look at it carefully, it's not a single bit, it's a bus, basically multi-bit signal. So here you have flags 3 down to 2, and here you have flags 1 down to 0. So why were they logically grouped together? Because NZ is affected by all instructions. CV is affected only by arithmetic instructions. Of course, the other requirement is to have a suffix S and for them to be data processing instructions. Yeah. So for data processing instructions, which are logical instructions, NZ is affected, CV is not affected. Whereas if they are arithmetic instructions, all NZ CV flags are affected. And that's why we grouped it as 2 groups, which doesn't mean you require only 2 flip-flops in total. It's total of 4 flip-flops. Okay, it's just that 2 of them have an identical write enable signal. So for example, flag 3 down to 0 is, let's say, following the order NSFCV, which means these 2 flip-flops have their values changed for logical instructions as well as arithmetic instructions. These 2 will be changed only by arithmetic instructions. That's the idea. And we already saw that it can be done through flag W1 and flag W0, which will be 1-1 for logical instructions with suffix S. 1-0 for logical instructions with suffix S, 1-1 for arithmetic instructions with suffix S. That's the idea. And you can see this flag W that is generated by the decoder is still conditioned by CONDEX. So this is an indication of whether a particular instruction is executed or not. That is, whether the condition is true or not. And if the condition is true, then the flags are affected, provided flag W10 is once in the first place. Yep. Now, where will you have a scenario where writing to the flags is conditioned by the condition, which eventually is dependent on the condition of the flags? Are we looking at a bit of a circular logic here? Are we? So my question is, see, the CONDEX is dependent on the state of the flags as well as the condition specified in the instruction. Like for example, if COND is 0000, it means the condition we are looking at or specified in the instruction is EQ. And that will essentially check whether the 0 flag, so here 0 is flags bit number 2. So if that is set, then CONDEX equal to 1. If 0 flag is set. But now I am using it potentially to affect the 0 flag itself. So there is something circular there. Is it okay? I had mentioned earlier that such circular logic is not okay, right? But here I am using it. Well, it's not circular because it's broken by a register. So if you look at it carefully, you can see that it's not like the output is affected by itself. So this affects this, but this doesn't affect this immediately. So this has an effect only at the clock edge. So 0 flag, even if it is supposed to be affected, will be affected only at the next edge, next clock edge. So in the current instruction or in the current clock cycle, we are looking at the value of 0 which was set by the previous instruction. Okay, and will be clearer once I write a scenario where this is possible. Let's say sub S R1, R2, R3. This will of course set the flags. In fact, all the flags depending on the result R2 minus R3. And now I can have a possible instruction REQS. Let's say R4, R5, R6. So now if R2 minus R3 is 0, then this instruction will be executed. And then we will effectively do R5 minus R6, store it into R4, and depending on the result of R5 plus R6. So depending on the result of R5 plus R6, it will also update the flags. And those flags are not checked by this instruction itself, but a subsequent instruction, which would be, for example, another instruction with a condition or a branch instruction with condition. You get the idea, right? So here is an instruction which both checks as well as sets flags. But it will check the flag or it will evaluate the condition based on the flag set by this instruction. And then it will set flags for subsequent instructions to use. Okay, so you don't have a scenario where an instruction is creating and using flag in the same instruction or within. Yeah, clear? I just explained it because, well, this is a very common confusion people have. And this is in fact one instruction that a lot of people fail to check in Lab 2. Okay, having an instruction which both sets flags and checks flags. Now the CONDEX is a Boolean value. It's actually a single bit which is generated based on two things. What are the two things? What is the condition specified and what is the current situation of the flags. And the correspondence between the two is somewhere in my first slide. Right? For example, if the condition specified is EQ, which is 0, 0, 0, 0, then the condition of the flag that we are looking for is whether 0 flag is set or not. And similarly for all the other 14 valid conditions, there are 15 valid conditions. The 16th one, 1, 1, 1, 1 is invalid because they are all complementary. So here it is always, so the complement should have been never, which doesn't make sense anymore. And if you understand how the flags are related to conditions, you understand computer arithmetic pretty well. Okay, so that's a homework exercise for you. Try and make sense of every single Boolean expression in this column and its correspondence with whatever is mentioned here. The condition called mnemonic. Yeah. Some of them are not quite trivial. You need to have a fairly deep understanding of number systems and what's going on, how you can generate carry, how you can generate overflow, etc. to be able to make sense of this. Okay, we will be in a better position to do that after we cover the first few slides of the next chapter, which is on computer. I will not be covering the exact logic here, but you will be in a better position to understand it after that lecture. Okay, now this completes our design of single cycle processor. So for example, here we have an OR instruction, and let's look at the various control signals that are asserted or not asserted by OR. So OR, let's say if it is something like ORR, R1, R2, R3, it's a DP register type instruction. Yeah? And then your branch control signal will be 0. Okay, it's not a branch instruction. Okay, assuming that its destination is not R50. And then you have, branch doesn't even look at it. Branch only checks whether it's really a branch, that is opcode 10, which obviously isn't the case. So branch is 0. BCS is what looks at R50. Yeah. Now mem to rec is 0 because the result is not the result or not the output from data memory. It's a result of the ALU itself because it's a DP instruction. So mem to reg is 0, so that the data is channeled this way. Mem w is 0 because it doesn't write to memory, it's not a stored instruction. ALU SRC is 0. Why is ALU SRC 0? ALU SRC is the one which is controlling this multiplexer. So we want the data to flow this way, so this should be 0. Because the second operand does not come from the immediate, it comes from the second register that is read. So the data should go this way because it's DP register type. And then we have IMM SRC, which doesn't matter because this instruction does not use an immediate. So whatever you give here doesn't matter. Which doesn't mean extend unit does nothing. In hardware, there is no such thing called does nothing, especially for combination circuits. Its output is an instantaneous function of input. So there is no such thing as do nothing. It's just that it's don't care. So we don't really care about how the bits from instruction are taken and extended because it's not going to be used anyway. Then reg W is 1 because it's an instruction which writes to register file. Reg SRC is 0, 0. What is reg SRC? Reg SRC is a 2-bit control signal which controls these two multiplexers. Okay, so bit number 1 of reg SRC controls what is the second register that is read, whether it is RD or RM. It is RD for STR, it's RM for DP register type. And since we are looking at DP register type, it's RM, that is bit 3 down to 0, that should go here. Okay, so this bit, so reg SRC bit number 1 should be 0. And once again, I have written, in this figure it's 1 and 0 written here, which does not mean, this bit is 1, it's just the bit index. It's a 2-bit value, so bit index number 1, okay, which you can say is the most significant bit, is supposed to be 0, because the data is supposed to go this way. And reg SRC bit number 0 should also be 0 to allow the data to flow this way. It is a hard-coded 15 only for GRAN instruction. For GRAN instruction, the first register read is R15, which is implicit, not explicitly mentioned in the instruction for GRAN, right? So that's why we have to hard-code it, and it becomes 1 here only when it's a GRAN instruction. And ALU OP is 1 because it's indeed an ALU operation. And please note that since it is DP register type, in the instruction format OP will be 0. Func 5, which is the I bit, is also 0. Okay, func 0 doesn't matter here. Okay, for now we are not looking at it, but it's a S bit. Now, how do we extend the functionality to include other instructions? In the labs, you will be doing a lot of that. We will start with this bare bones or very basic processor that we just talked about, and over the labs, you will be gradually giving it more and more functionality. Okay, so one thing that you will do in lab 2 itself is to be able to deal with CMP instruction. So for CMP instruction, the behavior is very, very similar to that of sub-S instruction. But one notable difference is that your destination register is not modified. So let's say if I have something like, say, CMP R1, R2. Is this R1 RD? No, it is RN and this is RN. So what is RD? CMP does not use RD because it does not write to a register. So what is there in the field corresponding to RD? RD is actually bits 15 down to 12 of the instruction. Can I look at those bits and say that, oh, it's a CMP instruction? No, because using 4 bits, the possibilities are 0 to 15, which are all valid and corresponds to some register anyway. So where do you incorporate the fact that the destination register is not supposed to be written? Well, CMP has a different func bits 4 down to 1, which is the CMD field. So the CMD field for CMP is 1010. It's not the same as sub-S. If it was the same as sub-S, you have no way to distinguish between sub-S and CMP. You can't really look at RD and figure out that RD is not supposed to be used. You get the point, right? Yeah. So CMD is different for CMP, and for CMP, the S bit is implicitly 1. But the ARM instruction format requires that it is 1. Though in some sense, when it is 1010, this has to be 1. It being 0 doesn't make sense, so in that sense, this bit is redundant, but ARM does not allow you to make it 0. If you make it 0, the instruction is invalid. Because we are looking at CMP, which is supposed to set flags, but then you are saying that flags are not set, right? So that doesn't make sense. So making it 0 will make the instruction invalid. Okay, so it's not optional to put it 1. If you follow ARM instruction set machine language, it has to be 1. And you don't write CMPS to make it 1. There is no such instruction as CMPS. CMP itself is only to set flags. Clear, right? Now, you see, we can identify that it is CMP instruction by looking at the CMD field. And if it is CMP instruction, the reg write is supposed to be 0 because it's not supposed to write to RD. So what will be there in the RD field? It's 15 down to 12. Well, in some sense it can be anything, but there again, ARM instruction format requires it to be 0000. Yeah? In fact, if you look into ARM instruction manual, that field is written as SBZ. Should be zeros. That's a requirement from ARM. Okay, otherwise the instruction is invalid. And the behavior could be, unpredictable. And whenever you have an instruction which is invalid, or if you are doing something you are not supposed to do, the ARM instruction manual will say what will be the consequence. And in many cases, they would have written the behavior is unpredictable. So if you supply an instruction which is invalid, yeah, so you are not supposed to do it. There is even potential for your processor going bonkers, doing something totally unexpected. Okay, so yeah, that's how it is. But this doesn't mean R0 is the one getting affected, because reg W should be made zeros. And how do you make reg W 0? When ALU decoder identifies that the operation we are looking at is CMD, it will assert a signal called no write. And when no write is asserted, reg write will be zeroed out. Because when this is 1, this is certainly 0. Because you see a bubble here, it means that if this input is 1, the output is guaranteed to be 0. Because after the bubble, it's 0. And if one of the inputs of an AND expression is 0, the output is certainly 0. Correct? So it will zero out reg write. That's the idea. Reg W or reg write. Basically, reg write will eventually be 0. That's the idea. Again, one classic mistake some of you guys make in lab 2 is not implementing no write properly. And the consequence of that is R0 gets modified even though R0 does not appear anywhere in your instruction. So it could be something like CMP R5, R6, and you will end up with R0 being modified. And some people might not even realize it if you don't test it properly. If your test case does not have a case which explicitly checks for this. And some people think, oh, R5 is not modified, so CMP R5 R6 works. No, you should actually check R0, not R5. because the RD field will be 0, 0, 0. You get the idea? Okay, now how do we implement register shifted register? That's probably one of the easiest things to do. All you need to do is just insert the shifter or insert a shifter into the data path, in fact into the path connect register to the input of the ALU. The input of ALU has to go through a multiplexer, so you just insert the shifter here. And this shifter will require 3 inputs. What are the 3 inputs? What is the type of shift? What is the amount of shift? And what is to be shifted? So what is to be shifted? The data read from a second register. The first register Rn cannot be shifted. Only the second register Rm can be optionally shifted. So that is the value to be shifted, 32 bits. Then SHAMT is the amount of shift, which is a 5-bit value which is there from the instruction directly, bits 11 down to 7. And then this is the type of shift, which is a 2-bit value, which specifies whether it is LSL, LSR, LSL, LSR, ASR, or ROR. And there is no change required for the controller at all. It's just purely a data path modification. Whereas CMP was purely a control unit modification. There is no modification required in the data path. Okay, and similarly and gradually you can incorporate more and more instructions, looking at what are the modifications that have to be done to data path and or controller. By the way, here I mentioned CMP as an example, but the same applies to other instructions like CMN, TST, TEQ, etc. And let me ask you this question: is the control unit of ARM processor a sequential circuit or a combinational circuit? It is sequential because it has some storage inside it, NSXCD. And any sequential circuit is fundamentally a state machine. Is it a Mealy machine or a Moore machine? Okay, now look at this. Is it a Mealy or a Moore machine? This is the part which makes it sequential anyway, right? The decoder part doesn't really matter because it does not determine the type of state machine. This is the part which does. Is it a Mealy machine or a Moore machine? Yeah, it's Mealy because you see your output is affected by inputs. And these itself are affected by the instruction, right? So your output is a combinational function of inputs as well as current state. The state part comes from here. So this is related to the state because this is derived from this. Okay, so it's not just based on current state, it also depends on current input. So this circuit is a Mealy machine. If you make it a Moore machine, you have to wait for one more cycle before you see the effect, right? Because a change in input has to cause a change in state to be reflected in the output. And for those who are interested in RISC-V, for RISC-V, the control unit is a combinational circuit because there is no storage of flags for RISC-V. RISC-V does not have processor flags. Sorry? So yeah, arguably simpler, but you pay for it by making your assembly language program possibly slightly more complicated. But from a hardware perspective, yes, it's simpler. But you also lose the ability to do conditional execution of instructions, which can be quite useful to avoid branches, because whenever you have branch, you will see soon enough control hazards, the requirement to do branch prediction, etc. It can cause branch misses. A lot of other issues associated with having too many branches. Okay. Whereas ARM has much less branches because of the ability to conditionally execute instructions. And that comes from condition code flags. It is not possible in this file. Okay, now let's look at the performance of a single cycle processor. Once the program counter value changes, that change will cause the instruction, the address into instruction memory to change. So the instruction that is fetched from the instruction memory will change. So the control signals generated will change, and some bits from the instruction will have to be used to read the register file. Then you have to do the operation, and the result of that operation for a load instruction will be your address sent to the data memory. The result of data memory comes in into the processor and eventually gets returned to the register file. So this is a complete path followed by the load instruction. One instruction, one cycle. That's why we call it a single cycle processor. So the moment program counter changes, so for example, if your clock is like this, so your PC changes immediately after the clock, and all this has to happen within that cycle, so as to make the data available to be returned to destination register ready by this clock edge or before this clock edge. And it is this clock edge at which PC increments. So the writing of the result to the register file as well as the incrementation of PC to point to the next instruction happens at the same instant, okay, which is the clock edge after the clock period during which that particular instruction is executed. So this clock cycle has to be long enough to accommodate this much flow of data. Okay, and no matter what technology you use, the data flowing through this many components within one cycle is bound to take a lot of time. Okay, even with the most modern, let's say 3 nanometer technology where transistors are obviously much faster, even then it's going to take substantial amount of time. Yeah, that's why we are going to do pipelining. Yeah, so we will look at pipelining. Again, many of you have some idea of pipelining, but we will look at pipelining in a lot more depth in chapter 6. Now, single cycle advantages are it's simple. If you call this simple, that is no data path resource can be used more than once per instruction, so some must be duplicated. So you need separate instruction and data memories because you can't really access the same memory for instruction and data in the same cycle, right? In one cycle, one particular component can do only one thing. It can possibly do another thing, but in another cycle, not in the same cycle. Okay, so that means that whenever there is a duplication of functionality, you need a duplication of functional unit or components. Okay, so here you can see you cannot use your program counter to increment, your adder or ALU to increment the program counter. Was it even possible? Can you use the same ALU to increment program counter? Yes, but not in a single cycle design. You could always come up with a multi-cycle design in which in one cycle it computes the result, in another cycle it's used to increment PC. It's possible, but you have to split or spread it over multiple cycles. And such a design is called a multi-cycle design. Whereas in single cycle, you have no choice but to duplicate components whenever there is a duplication of functionality. Oh, using multiple edges? We will see again one example for that sometime later, okay, where we use both parts of the cycle. But generally, it's not considered a very good idea to have, something being sensitive to two different edges. It doesn't help you because you are looking at edges, right? So even if it is something like this or something like this, what difference does it make? Because you are looking at only edges, right? Duty cycle becomes an issue only when you design something which is sensitive to both edges. Okay, which does happen. We will see one such design later in chapter 6. In fact, it's also used by DDR memories. Double data rate by looking at both edges. But there are issues as well. Okay, anyway, let's keep those discussions for another day. Now we have seen that the cycle time is limited by the longest instruction. And in our case, the villain is, the bad guy is LDR, right? Which is not too bad. When you compare it with some other more complicated instructions, like for example, floating point divide, if you try to fit it into one cycle, well, good luck to you, right? So, well, it's not very practical to do that. So we will see more details of how to make it more efficient in subsequent chapters. So we'll see pipelining in more detail, or in pipelining in quite a bit of depth in chapter 6. Then superscalar processing and another bunch of performance optimization techniques used by modern processors in chapter 7. And we will look at multiprocessor systems in chapter 8. So those are various ways to make things faster and better. Okay, so yeah, this is something that we will look at in more detail in chapter 6, pipelining. Some of you are new to it, some of you have some idea, but irrespective of whether you have a background or not, it's a very deep topic. There are a lot of pitfalls, a lot of issues to consider, and we will look at a number of them later. So that completes this chapter, and let's look at the next chapter, a very exciting chapter, arithmetic for computers. Well, computers are required to do computations, right? So we have to look at how we can design various computational or hardware which can do various types of computations. And when we talk about computations, we are generally talking about either logical operations or arithmetic operations. And there are again a lot of different types of arithmetic operations like addition, subtraction, multiplication, division, integer multiplication, integer division, then floating point arithmetic, so on and so forth. Yeah? Okay, so let's start with basic stuff, which is order. Okay, order is a component that is required standalone, or in many cases, that is for more complicated arithmetic operations, order becomes one of the steps involved. Like for example, subtraction is fundamentally addition with a negated second value, right? So a minus b is a plus negated version of b. That's how computers do it. And negation, unless otherwise stated, is 2's complementation. Then multiplication is fundamentally an addition operation. Okay, it is in the most simplest form. It's just repeated addition. 2 into 3 is 2 plus 2 plus 2. 2 added 3 times, right? But of course, doing that way will make it super inefficient. So we'll do it by doing shifting and adding, or by having an array of orders. But either way, you still need an order to do multiplication. Okay? And division is, in some sense, repeated subtraction with potential additions in between, depending on the division algorithm used. But there again, we can't really run away from addition. So addition is a very, very fundamental operation. So looking at how orders are implemented is important in that sense. Okay, now let's look at the so-called half order. I'm sure you had studied it in the whatever digital fundamentals module or digital design module that you must have taken earlier, right? Half order is just to add 2 bits. So let's say if the 2 bits are A and B, it's supposed to give you two outputs, which is the carry out as well as the sum. So it will find the sum of 2 bits, and if there is a carry, it will be reflected as a carry. And if it is 0, 0, well, sum and carry are both zeros. 0, 1, it is 0 plus 1, sum is 1, carry is 0. So sum is 1, carry is 0. 1, 0, again same story. 0, carry is 0, sum is 1. And when both the bits are 1, 1 plus 1 is 1, 0 in binary. So result is written as 0, or sum is written as 0 because we are doing a 1 bit mark. And whatever carry you have becomes, well, the carry, right? So pretty good, but except that in real life, it's very rare that you will be dealing with only 1 bit numbers. And when you have multi-bit numbers, you should have the ability to deal with a carry that is coming in from a lower significant stage. And you should have the ability to generate carry for a more significant stage. So you have carry in and carry out. So you have the 2 bits to be added, then there is a carry in, and you generate a sum and a carry. And it's fairly straightforward. Again, you are doing A plus B plus C in, okay, which is 0, 0 if all the bits are 0, and if there is only one of the bits which is 1, either A or B or carry in, which is the case here, here as well as here. So those are the 3 cases where one of the bits is 1, other 2 bits are 0. And in all the 3 cases, your sum is 1 and carry is 0. And next case is that of 2 bits being 1, exactly 2 bits being 1. And that happens here, here and here. So you are essentially looking at 1 plus 1, which is 1, 0. That 1 is carry, result is 0. And you are looking at 1, 0. And there is only one final case, one combination where all inputs are 1. So 1, 1, 1, and your sum is 1 and carry is 1. Now, if you look at the logic expressions for S and C out, you can see S is A XOR B XOR C in, okay, which is fairly easy to derive. Now, whenever you have a bunch of XORs, just count the number of ones. If the number of ones is odd, XOR is 1. If the number of ones is even, XOR is 0. Which kind of makes sense because whenever there are even number of ones or a pair of ones, they cancel each other. 1 XOR 1 is 0. Whereas if you have an odd number of ones, there will be 1 1 left out, which will not be cancelled by anything else. So your result will be 1. Okay, and in this case, 0 plus 1, or if the total is 1, well, you will have a result of 1. If the total is 3, again you will have a result of 1 with that 1 carry. Here it will be 0, 1, 1, 1. This is carry and this is sum. But whenever there are odd number of ones, your S will be 1, and that's XOR. And some of you might know how parity schemes etc. work, so there are some parallels to this. Okay, anyway, C out is AB or AC or BC. So what is a condition or situation where carry can become 1? Carry out can become 1 when there are at least 2 ones, right? Either of the 3 or at least 2 of the 3 inputs, that is either A or B or C in, 2 of them. If 2 of them are 1s, then there is a carry, because 1 plus 1 is 1, 0, which means there is a carry, right? So how do you write a logic expression for that? It's essentially the 3 taken in combinations of 2, okay, and you check whether there is at least one combination in which both of them are 1. And that would, if that is true, that means that there are at least 2 values which are 1. And that's what we do here. AB is one combination, AC is C in is one combination, BC in is another combination. So if any combination is 1, say for example AB is 1, it means that A and B are both 1. And then the result is either 1, 0 or 1, 1 depending on C in. But either way, you are carrying 1. That's the idea. Now addition is also required not just for arithmetic operations. There are other scenarios where addition is required. Like for example, counter. A free running counter is essentially a register plus an adder, where the current value in the register is taken, added with one is added to it, and then stored back into the register. So counters are fundamentally register adder combinations. And there are other scenarios where adders are required, like for example address decoding, especially if you do it in a sort of a hierarchical manner. Like for example, you issue an address to the memory, and the memory has to figure out the exact location. Or if there are multiple physical hardware which forms the memory, you have to figure out which physical hardware it is supposed to be diverted to. Which is indeed the case for your lab, right? Your data memory is composed of 3 parts. Which are the 3 parts in your lab? Data memory. You have a constant memory, you have a variable memory, and then you have memory map peripherals. So all 3 are in some sense part of the so-called data memory. So the hardware that we design should eventually be able to look at the address range and figure out which hardware block is to be activated. Is it constant memory or variable memory or memory map peripherals? And 3 are entirely different hardware. Constant memory is, well, a read-only memory. Variable memory is a RAM. Read-only memory can have contents on our own. RAM has no useful content on power. But you can write to RAM and then read from it. Whereas read-only memory, which is a constant memory, cannot be written to. And memory map peripherals are a whole different story altogether, which we will look at in chapter 8. Yeah? But you see, to figure out which component is to be activated, you might require decoding, and addition can be a useful step when it comes to decoding. And it's also required for comparisons, etc., which happens both at the word level and possibly at lower levels as well. Word level CMP instruction fundamentally does subest, right? Subtraction is in fact addition. Addition with the negative of the second point. So yeah, you can see you can't really get away from addition. That's my point. Yeah. Now, how do we deal with, or how do we have 32-bit numbers? How do we deal with 32-bit numbers? Let's say. Well, one option is you can cascade 32 full adders together, and here C0 will be 0 because there is nothing that is coming in. But having said that, we will see later that in subtractor this C0 is useful and it's not 0. But yeah, for now, looking at addition, yes, C0 bit is 0. But well, you have two 32-bit inputs, that is A and B. A is A31 down to A0, B31 down to B0, as well as C0, and then you generate a 32-bit sum, which is sum 31 down to 0, and there is a carry C out. And if it is an add as instruction, the C out is what goes into the carry flag. Yep. So all we need to do is simply cascade it, which looks simple enough, and indeed it is simple. It's just do it once and duplicate it 32 times, right? Well, that simplicity usually comes at a cost, right? And what is the cost here? It takes a really long time. Okay, and if you do it, and if you are looking at a high-speed circuit, it could very well be, or very likely be, a part of your critical path. Now, each unit here is essentially a combinational circuit, right? A combinational circuit with 3 inputs and 2 outputs. And generally, a combinational circuit can be thought of as a 2-level logic. In fact, every combinational circuit can be implemented as a 2-level logic. An AND layer and an OR layer. Like for example, if I want to have like A1 B0 or A0 B1 for whatever reason. Okay, so you will have a product layer and a sum layer. If you are doing product or sum expressions. If it is sum of product, sorry, sum of product. It's a sum layer here and product layer. Okay, so this is a sum of product expressions. And if it was something like, say, A0 or B0 and A1 or B1, something like this. Okay, not meaningful expressions, just showing you. This is a product of some expression, and then here you will have OR layers, and finally an AND layer. As many AND gates as the number of outputs, and here as many OR gates as the number of outputs, and here it's a single expression, so a single OR gate. But a single OR gate does not mean it's a two-input OR gate. If there are a large number of so-called product terms, you are looking at a multi-input OR gate. But my point is, any combinational circuit is a two-level expression. So for now, let's keep it as two-level. So how many gate delays do you have to implement a 32-bit circuit? It is slightly meaningless to talk about gate delays or the number of gate delays for some reasons that I will talk about later. But for now, let's assume that it is relevant. Yeah, it's simple, 2 into 32. So you are essentially looking at the number of delays increasing linearly with the number of stages or the number of bits. So if you are looking at a 64-bit adder, you are looking at 128 gate delays. Okay, assuming 2 gate delays per unit. Which doesn't sound very good, right? 128 gate delays, that suddenly feels quite a bit. Is there a better way? Well, if you are looking for minimizing cost, there is no better way than this, because it can't get any simpler than this, right? That operation has to be done, so this is a minimal possible number of gates or hardware to do the operation. So if you are creating a toy for your kid, go ahead and do this, but not if you are looking at a high-speed, high-performance computer, right? And that's where carry look ahead comes into play. There are quite a number of variations for carry look ahead, but the fundamental idea sort of remains the same. Well, here, if you are looking at, let's say C31, you are looking for the carry to propagate through all these stages in between, and that's why it takes time. Is there a way to generate a higher order carry directly? So let's say if for some reason you could generate C31 without really having to wait for that long. Let's say for some reason you can generate it within 15 cycles. So 15 gate delays. I'm not talking about cycles, sorry. We are looking at combination circuits, nothing sequential here. So right now it requires a lot of gate delays, right? What if we can bring it down to something like 15? Then it's good news, right? In 17 clocks, so 17 gate delays, you have the output. Because once this is there, 2 more delays later, you will have these 2. Because each block is 2 delays, right? But that is provided you can somehow generate C31 without really waiting for it to be rippled in. So the question is, can you? Well, theoretically yes, because eventually C31 is also a combination circuit, generated by a combinational circuit. And I had mentioned that any combinational circuit can be implemented as a 2-level logic. Okay, so theoretically it's possible to just have 2 logic layers and generate C31 directly. Sounds too good to be true, right? And it is. So it's not true, right? So what's the problem with that? Okay, let's say you are looking at C1. Write an expression for C1, which we already did. It is A0, B0 or A0, C0 or A0, B0. How about C2? How do you write C2? It is A1, B1 or A1, C1 or A1. Okay, here it should be B0, C0. So B1, C1. Now we already have an expression for C1, right? So just substitute it here. And you will get C2 is A1 B1 or A1 into, or not into, and A0 B0 or A0 C0 or B0 C0 and B1 and this whole thing again. And now you see, you have C2 purely as an expression of C0 and AIs and BIs. And in this case, AIs, A1 I0 and BIs is B1 B0. And you can already see that for C2 itself, things are getting out of hand, quite big. Imagine how many terms will be there for C31. The number of terms and the number of inputs to each term grow very fast. So the amount of complexity that you are looking at grows exponentially with the number of inputs or bits, which makes it impractical. Right? The problem is you will have too many terms and each term is big, which means that you are looking at gates which have too many inputs. Like imagine the plight of the last OR gate that generates it. The number of inputs to that OR gate will be growing exponentially with the number of inputs. And bigger gates are slower. Anything bigger is slower. That's a law of, or that's a reality of the nature, right? So you will have large number of gates, each gate having a large number of inputs. And a 2-input gate and 3-input gate are not entirely comparable. And as the number of inputs grow, the delay associated with the gate will grow as well. And now you have only 2 levels of logic, but each level having impractically huge gates. So, well, doesn't seem to help much, right? Well, but the idea is useful. It's just that you can't really scale it all the way to something like 31. You can scale it to a smaller level and still generate carry fast. But even then, this is kind of inefficient. You can see for C2 itself, it's already getting out of hand. Imagine C3, imagine C4. And for C4, well, we are only looking at a 4-bit, right? Only 4 bits. And C4 itself is going to be very huge. So that's why, instead of just doing things the brute force way, let's have a step back and see what exactly are we trying to do. Is there some logic which allows you to simplify this whole thing? So we should look at when a carry is generated and when a carry is so-called propagated. So if you look closely at any particular stage, that is, if you look at a full adder, you will see that the full adder generates a carry if both the inputs are ones. So both inputs should be ones for a stage to generate a carry. And when we say generating a carry, the carry output is for that stage is guaranteed to be 1 irrespective of the carry input. Because the stage generates a carry, so it doesn't matter whether the carry is rippling in or not. With respect to carry output, we are looking at carry output, yeah, not at the sum. So a stage generates a carry if both the inputs are ones. Now a stage propagates a carry, that is, it might not generate the carry from the inputs, but if there is a carry in, there is a carry out. That's what we call propagating a carry. So a stage will propagate a carry if either of the inputs is 1. If it is 1 0 or 0 1 or 1 1, these are the inputs AI and BI. In all the 3 cases, if there is a CI, there will be a CI plus 1. Or if CI is true, CI plus 1 will be true. Makes sense, right? So this is what we call the propagate condition, or the condition for a stage to propagate a carry. Now we can write C1, C2, etc. C1 is B0, C0 or G0. That is, stage 0 generates a carry, and this is when A0, B0 is 2. That is, A0 and B0 is 2. Then the stage generates a carry. Or if C0 is 1 and the stage propagates a carry. And for condition for propagation is that either of the inputs is 1. And in this case, A0 or B0 is 1. Either of them is 1. If both are 1s, well, it's going to be generating as well as propagating carry. So the carry will be 1 anyway. So either the stage generates a carry or the stage propagates a carry from the previous stage or the carry input. And C2 can be written as P1, C1 or G1. Either the stage 1 generates a carry or stage 1 propagates a carry from the previous stage or the carry input. So this is C2. Now you already have an expression for C1 which can be substituted here. And you get P1, P0, C0 or P1, G0 or G1. And this already looks much saner as compared to this C2 expression. Right? So here we were blindly following it or blindly writing the combinational expression, whereas here we are using some brains. And that certainly simplifies the complexity. And you can see that complexity is simplified by the fact that certain things are not generated over and over and over. So here you see there is P1, there is P1. P1 is generated using just one gate. P1 is nothing but A1 or B1. Right? The condition for stage 1 propagating a carry. So you generate it once and use it as many times as you want. Whereas here, in some sense, we were doing the same logic but generating it multiple times. So that expression for P1 appears at multiple places in array. And that's why things went out of hand very quickly. Whereas here, by looking at the logic, we are trying and we are eliminating unnecessary logic by doing a pre-processing of inputs. Okay, now it looks like there is now 3 gate delays to generate each of these. Why 3 gate delays? Oh, sorry, 2 gate delays to generate each of the carry. So 3 gate delays to generate the eventual sum. Okay, because C2 will eventually be used for S2, right? S2 is a function of C2. C2 is a carry into stage 2. S2 is the output of stage 2, right? So C2 itself requires 3 levels of logic, 1, 2, because each of this require 1 level of logic, and then you have a sum of product expression which requires 2 further levels of logic. So you have 3 levels of logic to generate C2, and 2 more levels of logic to generate S2, because your S2 is a combinational expression of C2, so it's a 2-level logic. Yeah. So now you see you are in some sense having more levels of logic, but you are looking at simpler expressions. Now, whenever I talk about this levels of logic, etc., it's just to give you the feel of things. The exact number doesn't really matter. Yeah, just to give you a feel of how many levels of logic are there. Because each level of logic might have a variable delay depending on the size of the gates, etc. So it doesn't make a perfect sense or perfect correspondence with a real physical delay. But still, this picture is good because it gives you a sense of scalability of things. Kind of similar to order of whatever for your algorithm, right? That doesn't give you an exact number or exact amount, but it gives you a sense of scalability. So these numbers that I am talking about is just to give you that. I won't ask in the exam like how many gate delays are there exactly, but you need to have a sense of the trend. That's right. So what I'm trying to say is each of these PIs and GIs require 1 gate to generate. So P1 is nothing but A1 or B1. P0 is A0 or B0. Okay, and G1 is A1 and B1, and so on. So one level of delay here to generate each of these terms, and a further 2 delay to generate C2, for example. And it's the same case for all CIs, assuming that we are generating all CIs using this kind of expressions. Okay, GIs and PIs generating CIs. So you essentially have 3 levels of logic before all the carries become available. And once you have all the carries, another 2 levels later you have the results. Because to generate a sum from the carry, you are essentially looking at a 2-level logic, which is implemented by your full adder, right? So technically in 5 gate delays you can compute all your results. Sorry, is it 5? Yeah, 3. Yeah, 5 gate delays. But here again you have a problem. C2 is already, well, not the simplest of expressions. C3 is definitely going to be complicated. C4 is even more complicated, and C31 will be very complicated. A lot better than the previous case where we mindlessly just expanded the expressions. This is certainly an improvement, but still we are looking at huge circuits. So generating something like C31 directly will be impractically huge as well. So are we back to square one? Not exactly. We already made some progress, but not as much as we would have liked, right? So what we do is, one possibility is create a 4-bit block. Within the 4-bit block, all the carries are generated directly without having a carry propagation from the previous stage. So here we are looking at a 4-bit adder. So you essentially have 4 full adders, but the carry doesn't really ripple through. Instead, all the carries required are generated by the so-called carry look-ahead unit, which will take in G0s, G0, P0, G1, B1, P1, G1, etc. These are essentially PIs, small PIs and GIs, which require 1 gate delay. So 1 gate delay later, all these are available. 1 gate delay from the point these inputs stabilize. All these are available. And 2 further gate delays later, you have all these available. Even C4. And once you have this, 2 further delays later, you have S3. So now S3 is available in 5 gate delays. How about if it was allowed to ripple? It would have been 8, right? Because each stage has a 2 gate delay. So 2 plus 2 plus 2 plus 2, 12. It scales linearly for ripple carry adder. So it would have been 8. Now we brought it down to 5, which looks like an improvement. Now how about for 32 bits or 16 bits, for example? You cascade 4 of them. So there is still rippling of carry between blocks, but within a block, rippling is avoided. So that is, for each stage or unit of 4, there is no rippling within, but there is still rippling between blocks. So how long does it take, for example, to generate S15? S15 is the sum, the most troublesome sum to generate for 16-bit numbers. It is, A15 down to A0 plus B15 down to B0 plus C0. So how many gate delays does it require with rippling? Well, it's not very intuitive to compute. It's in fact 3 to generate C4, and then it will be going to the next carry look ahead unit, which doesn't require 3 because all these would have already stabilized there too. So it's actually 3 minus 1. So it's 3 plus 2 for the next stage, plus 2 for the next stage, and that will allow the last stage. Now we have 4 stages, right? So the last stage carry input. So once that stage has a carry, how long does it take for the result to appear? Once this is stabilized, 2 further delays to generate this one for the last stage, which is the stage which deals with or generates S15, and another 2 delays to generate S15 itself. So it would be something like this. So that's 11 gate delays. Now, is there a better way to do it than just cascading 4 such stages? Well, we can do a carry look ahead at a higher level. So now each block here is something like this. And we have a carry look ahead at a higher level. Now, how does this work, this carry look ahead circuitry? Each stage here, in addition to generating the various carries, can also generate a block generate and a block propagate. Will this block generate a carry? Will this block propagate a carry? And how can you get expressions for that? Simpler than you think. P0, that is whether this stage, this is a stage which deals with bits 3 down to 0. This stage will propagate a carry if all the 4 substages, single bit stages, propagate carry. All of them have to be sort of transparent for the whole thing to be transparent, right? So it is just nothing but the product or the AND of all the propagates. Now, will this stage generate a carry? Yes, if the most significant stage within that or substage within that generates a carry, or the stage which is one level below, which is stage 2, generates a carry which is propagated by stage 3, or if stage 1 generates a carry which is propagated by stage 2 and eventually by stage 3. So that's idea behind this expression. So now we have block propagate and block generate. And once you have block generate and block propagate, you can use the exact same circuit. This is in fact a photocopy of this. Exact same circuit. Doesn't require any more or any less number of gates. It's the exact same circuit that you have here, which will generate something like C16 and C12. This is just a 2-level logic, identical to the previous 2-level logic here. Because you see, after all, these are all single bits. Even though it comes from a block, it's after all a single bit. So the processing done to generate the various carries is exactly the same. And with this, compute the number of gate delays. Well, now things become even more complicated to compute, right? You can do that and you will see that it will be 9. So if you had allowed rippling between blocks, it would have been 11, and now I think, if my memory serves me right, it's 9. How about for 64-bit case? You can consider this as a fundamental block and either cascade 4 of them or generate a higher block level generate and propagate, and then have a circuitry which is identical to this at a higher level. Yep, that will be taking in C0, C16, C32, C, what is it? 32 plus 16, 48, and will generate the corresponding carries. And once the carry is generated, like for example C12 is generated, it will further have to go through the next level carry look ahead unit here, and eventually into the individual pull orders. Got the idea? So here, after all, this block is this block, right? So once you have this carry coming in, it still has to pass through the carry look ahead unit and the individual pull orders before you get the output. And same goes for the higher level. And again, if my memory serves me right, for 64-bit case, you can get the result within, I think, 13 gate delays. As opposed to a pure ripple carry adder, which would have required how many gate delays? 64 bits, 128 gate delays. So now we are down to 13. Okay, and you can see the pattern is something like 5, 9, 13. For this was for 4-bit case, 16-bit case, 64-bit case. The original delays would have been that is with triple carry 8, 32, 128. So instead of growing linearly, now the gate delays are sort of growing logarithmically. Right? With each power of 2, you essentially have 4 levels of logic order. So it's logarithmic. So yeah, now it looks a lot better, right? And that is carry logic addition. But once again, I put in all these numbers just to give you a sense of how things grow. These numbers don't make a complete sense because one gate delay for a ripple carry adder and one gate delay for a look ahead carry adder is not the same, because for look ahead carry, the gates are a bit more complicated than ripple carry adders. You have multi-input gates involved, right? Like for example, to generate this, you are looking at a 4-input gate, which simply wasn't there for ripple carry adders. Yeah. So yeah, you get some sense of it, right? And that's all that is required. These exact numbers, first of all, don't really make sense. Second, are all pretty hard to compute as well. Okay, so now something for you to think about. If it is 32-bit, how will you deal with it? Will you cascade 2 16 bits, or will you have a higher level carry look ahead logic? Think about it. Okay, now let's move on to subtractor. Subtraction is fundamentally addition. So once you have an adder, converting into a subtractor is very, very easy. So if you have, let's say, an n-bit adder available, to generate an n-bit subtractor, so which does a minus b, what you can do is take an n-bit adder, then add the 2's complement of b. How do you add the 2's complement of b? Flip all the bits of b and add 1. And the facility to add 1 is already there. We already have the facility because for a normal adder, C0 is 0. There is no carry into the stage 0, into stage 0. So we can make use of that C0, just make it 1 if we are supposed to do subtraction. Okay? So that part is done. Now how about flipping all the bits? This is essentially a plus 2's complement of b. That is a plus b bar, that is b prime, flipping all the bits plus 1. So you have to flip all the bits of b and add 1. And to flip all the bits of b, well, all we require is a not gate or, again, even though I drew only 1, it's in fact n not gates, because each bit of B is supposed to be flipped individually. Okay, in one of the exams, I had this statement which was supposed to be identified to be true or false. You require only one NOT gate to convert a 32-bit adder to a 32-bit subtractor. A lot of people said yes, true. And that was based on this diagram, but you are at a stage where you don't really look at the gate as a gate, you also need to look at the bit width. And if the bit width is n, you are essentially looking at n gates, not one gate. Yeah? But yeah, the circuitry is pretty simple. Now let's create a complete arithmetic and logic unit which can do addition, subtraction, and OR. These are the 4 operations supported by our basic ARM processor, right? So let's have a look at the circuitry for this. By the way, the circuitry for RISC-V or whatever processor will be the same, as long as it's a same 4 operations. Okay, so how do we do it? ALU control bit number 0 is the one which distinguishes between addition and subtraction. And it is 1 for subtraction, 0 for addition. So that bit can be directly given as C0 or carry input. Because carry input is supposed to be 1 when we do subtraction. And for subtraction, bit number 0 of the ALU control will be 1 anyway. Yeah? So bit number 0 of ALU control can be given directly as C0, which will be 0 for addition, 1 for subtraction. Now we have to select either B itself or the ones complement of B or bit flipped version of B, depending on ALU control bit 0. If ALU control bit 0 is 0, we should not flip the bits of B because the operation is addition. So if we give C0 is supposed to be given here, not there. Yeah? Because this is our adder, not this. This is a multiplexer. So for the multiplexer 2, the select input should be 0 for addition, so that B without being complemented will become the second input to the adder. This is the adder that we are using. Whereas if ALU control 0 is 1, that is for subtraction, we have to use the bit flipped version or the ones complement version of B. So we pass it through NOT gates, n NOT gates for bit width of n, and this is a bit flipped version of B or B bar, which will be selected if this bit is 1. That is if the operation is subtraction. So now we have achieved conditional complementation and conditional addition. So add 1 if operation is subtraction, which means you can straight away look at bit 0 here and use it as C0, so conditional addition, and here we achieve conditional complementation. Yep. So yeah, we are done with having a circuit which can do addition or subtraction depending on ALU control bit number 0. By the way, this circuitry, if implemented directly, is a bit of an overkill. A much simpler way to implement this is you can use an XOR gate for conditional complementation. So if this is B and this is ALU control, right? So let me just call it let me just call it X for now. X is nothing but ALU control bit 0. So what is the output here? If X is 0, your output, let's say Z. Okay, Z is B if X is 0. It is B bar if X is 1. That's what you want, right? And this is XOR logic. So you see, if the control input is 0, your output should be left as such. Output should be the same as input. If the control input is 1, then output should be complemented. So that's XOR logic. Clear, right? So you can implement it using just 32 XOR gates for 32 bits. But that is a simplified logic which you don't really have to write when you write HDL. You can simply write like this and let the synthesis tool do the appropriate optimization. Whereas if you are implementing it using discrete gates, like for example, there are those TTL ICs available, 7.4 series ICs. So if somebody hates you and requires you to implement a 32-bit AND bar subtractor using TTL gates, which will take you several days, by the way, to wire it up, well, then you should be using XOR gates. But gone are the days where you will use separate chips to implement each logic gate. So these days, what we do is write HDL code, implement it on an FPGA or ASIC depending on your volume and target application. And then you can simply follow this logic, okay, and let the synthesis tool do the rest. It might actually be better not to simplify it on your own, because the tool can generally do a better job than what you do. And sometimes if you try to come up with some funny expressions based on simplification, the tool might not be able to simplify it further. So it's better not to simplify too much. Yeah? So yeah, that completes this part. And now these are given to, let's say, a multiplexer. The multiplexer will select the same result if ALU control is 0, 0 or 0, 1. Because if ALU control is 0, 0 or 0, 1, it's addition or subtraction. And addition and subtraction are both coming in from the same unit. It's the same order that generates the sum and the difference. So in both the cases, your ALU control, that is when ALU control is 0, 0 and 0, 1, you use the same value. But this value itself, of course, will be different depending on whether it's addition or subtraction. But the difference is through some changes here rather than here. How about for and or expressions? And or are very simple in hardware. If you have 32-bit AND operation, it's just 32 AND gates. 32-bit OR operation, again 32 OR gates. So this is 32 OR gates, 32 AND gates. So the result of bitwise AND will be selected and becomes your result if ALU control is 1, 0, which is corresponding to AND. 1, 1 corresponding to 1. Fairly straightforward, right? But again, this overall circuit can certainly be simplified, which you can leave to the synthesis tool. Okay, yeah, so I guess you are probably saturated enough and you need a break. So let's come back here by 7:45. I know some of you or many of you won't fancy this 3-hour lectures, but since this module is offered in the evenings, you can only have a 3-hour slot. You can't really have 1 2-hour, one separate 1 hour, because that will require people to come back in the So once it is fabricated, they will test chips. Okay. If they find that some chips have this kind of whole violation, they will put it into the They can't do anything about it. But if there are setup violations, they will just reduce the clock speed. They will disable some parts of the chip and sell it as a lower end chip. Yes.
And then this and
For all we know, I5, I3, I5, I3, and I7 could be the exact same. But for I3, they just disable some parts and lock it down. It goes to wasteland. So the process is called binning, where they will characterize or find analyze the circuit, put it into various bins. One of them is a waste bin, and that will be and that's why you might have, I think I mentioned it in the class, right? I think lecture 1. I have mentioned that sometimes the graphics card that you buy sometimes it can't work. That depends on how much margin you have. If you are lucky, you might be buying a product which has a higher margin, which allows you to run it at a higher frequency. Yeah. But the variation is not too huge because its characterization is done at the factory level, and they have already differentiated products at that level. But even within the same level and same print, there could still be some variation. And if you are lucky enough, you might be able to explore it. It's called silicon lottery. Silicon lottery. Yeah. Even within the same die, which is subjected to the same process, there could still be some variations here and there. Because the concentration of the so-called impurity is like, it might not be that uniform. Yeah. And again, the sizes, etc., that depends on the so-called mass. Yeah, and the mass might not be like perfectly same thickness everywhere, etc. And the beam of light used again could have some slight variations in power. All this can cause variations. Yeah, sometimes it is 0, but first no, nothing stops you from writing your own. Like you get the initialization call for your own, right? Okay, and if you want to play the hardware is like you can just change bits 15 down. That is just changing one head from 0 to something else. You can see that the similar rules are made 0 to 6. But you can manually change it if you want in the head file and flash it. Then of course you are on your own. Because you are doing something with the already on hand. The same bit is used 2 times. One is to control the multiplexer, one is to extract the what are any control? Let 0 combined, but there is no such thing as a free input multiplexer. So here we are giving any control. So this material doesn't really matter. I remember learning. Okay, folks, welcome back. Okay, welcome back. So we had seen how an ALU that can do addition, subtraction, and or is generated, right? And some of you have this confusion about why the two inputs are essentially fed with the same value. The point here is addition and subtraction are both done by the same unit. The result here will depend on whether the operation to be performed is addition or subtraction, and that is distinguished by ALU control signal. So the output of the adder is in fact the sum for add operation, the difference for subtraction operation. So this can be thought of as a 3-to-1 multiplexer. But there is no such thing as a 3-to-1 multiplexer. So it's a 4-to-1 multiplexer where the two inputs happen to be the same. So let's say if the operation is addition, this will be a plus b and it will be passed this way. If let's say the operation is subtraction, that is when this bit is 1, it's a minus b here and this will be the one passed. Okay? So it doesn't cause any issue for the result. And this, not that is a single bit. Okay? The same bit is given here and here. Here it's to select the complemented or non-complemented version. Here is to act as the carry input. So that plus 1 part. Now this is still 2-bit because to distinguish between and or you still require the significant bit of the selected. Now let's talk about NSR-CV flags. If the result is negative, n bit should be set. So the ALU does not really set bit, it only generates the flags which may or may not be stored, depending on the condition S. Right? If S bit is specified, it will be stored, otherwise it won't be stored. But ALU generates the flags anyway. Now, n bit or n flag is the easiest. It's just the most significant bit of the result. So whatever result you have here, which could be the result of addition or subtraction or AND or OR. Whatever that is, the most significant bit is your sign bit. So what if you are dealing with unsigned numbers? But the hardware doesn't know whether you are dealing with signed or unsigned. The operation is the same. The hardware which does signed or unsigned is the same. There is no way to distinguish between signed and unsigned. Because AND instruction is just AND. There is no AND unsigned versus AND signed. So the hardware does the exact same thing. And since the hardware doesn't know whether you are dealing with signed or unsigned numbers, the end flag will be set if the most significant bit is 1. And as a programmer, it's your responsibility to make sure that you don't look at end flag if you are dealing with unsigned numbers. Because for unsigned numbers, end bit doesn't really make any sense. Okay? And if you look at this slide, you can see wherever there is a mention of unsigned, you can see end flag is not checked. So for example, here unsigned higher, unsigned lower or same. You see n is not there at all. And here you have unsigned. There is nothing about n. So let's say if you are doing sub S R1, R2, R3. And let's say if R2 and R3 are supposed to contain unsigned numbers. And if your next instruction is something like BCS, it is okay. Whereas if the next instruction is something like, let's say BMI, you are doing it horribly wrong. Because R2 and R3 are supposed to contain unsigned numbers, which means the subtraction that you did is an unsigned subtraction. And then checking the sign of the result doesn't make sense. Because your result is unsigned, so it doesn't have a sign. Right? And then you are checking the sign here. BMI is checking the sign. Because you see, it's looking at MI. That's the idea. So essentially, if the operation is unsigned, or if you are dealing with unsigned numbers, the N flag and V flag makes no sense at all. Because there is no concept of overflow, there is no concept of negative for unsigned numbers. So for unsigned numbers, shouldn't be looking at this, whereas the C flag and V flag are both sensible, and so C and Z. They are both sensible and potentially useful. Because carry is important for unsigned numbers. Well, for signed as well as unsigned, a 0 is a 0. 0 has the same representation irrespective of whether you are dealing with signed or unsigned numbers. So 0 is one flag which is equally applicable for both. Okay. For signed numbers, n is useful, v is useful, c is not, and 0 flag is useful. Carry doesn't tell you anything about the correctness when it comes to signed numbers. So that's a connection. And here we can see that as well. Wherever there is mention of signed, it wouldn't be looking at carry. Whenever there is a mention of unsigned, we wouldn't be looking at overflow or negative. But 0 is applicable for both. Now 0 flag if all the bits of the result are 0. Okay, once again, the computer or the hardware doesn't know, so it's up to the programmer to make sure that you check only those flags which are sensible for the type of data you are looking at. 0 flag, well, is sensible for both, and even otherwise, well, if the result is 0, 0 flag is set. C, or before we go into Z, C, let's look at that once again. How do you identify if the number is 0? So if S31 down to S0 is 0, then 0 flag is supposed to be 1. If, okay, so Z is equal to 1 if S31 down to S0 is 0. So to check this, you can have a big OR gate with a complemented output. So if all the bits are 0, this will be 0 and this will be 1. If there is any bit which is non-zero, so let's say if this is 1, this will be 1 and this will be 0. Okay, which can also be drawn like this. Because this is exactly the same as this. De Morgan's theorem, right? So A or B, the whole bar, is A bar and B bar. So it's the same thing. And that's exactly what we have here. For generating 0, we need to have a 32 input NOR gate, which is nothing but an AND gate with complemented inputs. And negative flag is just bit 31 of the result. So we are done with this, we are done with this. Now carry is again very simple. Carry is simply carry out of the order if the operation is addition or subtraction. Carry doesn't make any sense for logical operations. Carry is something which is related to arithmetic operations. So if it is an arithmetic operation, and how do you determine if it is an arithmetic operation? ALU control bit 1 will be 0 for arithmetic operation. So for arithmetic operations, carry is simply the carry out of the order. Doesn't matter whether it's addition or subtraction, it's simply the carry out. And we just check and ensure that we set carry only for arithmetic operations, not for logical operations. But in reality, this AND gate is not very essential, because even if carry is generated for logical operations, it won't be stored anyway, and that will be ensured by your control unit. Okay, so in that sense, this logic is a bit redundant, but I'm just following the one from textbook. Yeah. So yeah, this is just to ensure that only arithmetic operation will have a non-zero carry. Logical operations will have carry equal to 0. Now, the meaning of carry is a bit interesting when it comes to subtraction. The same carry bit is used as carry. So, is carry the same as borrow? What do you mean by borrow? Let's say I have a number 0011 and the other number is, so let's say this is A, this is B is 0111. Do the subtraction. 1 minus 1 0, 1 minus 1 0. This is 1 0 minus 1 1. And here it is, what is it here? It was 1 0, 1 was taken here, so what you have 1 here, what you have is 1 here, so 1 minus 0, 0. Sorry, 1. And you have a borrow here. This is the conventional subtraction, right? You borrow it from the left if the second one is larger. So here it was 0 minus 1, which can't be done, so you borrow 1 from the left, and that's why you have 1 0 minus 1 is 1. Yeah. Now things will be a bit interesting now. So 0 0 1 1. How exactly is the operation performed in hardware? It's not like this. This is your conventional subtraction. And in conventional subtraction, you have a 1. And that makes sense because you are subtracting a bigger number from a smaller number. So there is bound to be borrow. Right? And that's why there is indeed a borrow from the left here. Now, how do you do the actual arithmetic in hardware? It is B bar plus 1, which is 1 0 0 0 plus 1. 1 plus 1 0. There is a carry. 1 plus 1 0. There is a carry. That 1 is here. That 1 is here, and nothing comes out. There is no carry.
But even if there's a carry, it's not.
Well, it can be discarded if you know your 32-bit result is correct. But we don't, and that's why we have to care about carry. But here you see, when you do conventional subtraction versus when you did it the hardware way, that's how the hardware will do it. You can see the carry and the borrow are not the same. So here the carry generated is nothing but the complement of borrow. And indeed, in ARM processors, carry is a complement of borrow. So if you are subtracting a bigger number from a smaller number, there won't be carry. There is borrow, so there is no carry. Yeah, which can be quite confusing. But that's how the hardware does it. So it makes logical sense. Okay, so that's carry. So we don't have to really distinguish or do any manipulation to carry depending on whether it is addition or subtraction, because ARM does it the hardware way. For Intel, I believe it's the other way around. So you need slightly more complicated circuitry than this. Because when there is a borrow, the carry flag is actually set in Intel, whereas a carry is cleared in ARM. Now, last one is more complicated, or the most complicated one, overflow. Now, carry and overflow are things that people confuse between quite often. Now, let me illustrate the difference using 3-bit numbers. Okay, 32 will be too much, so let me deal with 3-bit numbers. Using 3 bits, how many possibilities are there? 8 possibilities, right? So 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1. And what are these corresponding to? The decimal equivalents? That depends on whether we are looking at signed or unsigned. So let's follow unsigned for now. So that will give me 0 1 2 3 4 5 6 7. What if it is signed? Then this is 0 1 2 3. So that part is the same, right? Positive numbers have the same representation in both. Now this is -4, -3, -2, -1. Not very hard to do. You might know the trick. So let's say if it is 1 1 0, look for the first one from the right, write down everything, complement everything to the left. So this is 2, sign is negative, -2. So basically you have to undo 2's complementation of 1 1 0, or undo 2's complement of 1 1 0 to find the magnitude. And the magnitude is 2, sign is negative, so -2. Now, let's say I am doing 2 plus 1. How will I do it? Remember how you did in your primary school using number lines? If you are required to do 2 plus 3 or 3 plus 2, you first mark 3, then go 2 units to the right? And then you will reach 5, and that's how you do addition using number line. Here it's the same, except that it goes in circles. Yeah, so let's say 2, so you mark it here, and then go 1 unit to the right, and you get 3. That's how you do arithmetic using number circle. And here, why is it number circle? Because it wraps around. You have only finite number of possibilities, so it wraps around. Everything is cyclical, right? What goes around comes around. Now, is there a problem when you do an arithmetic? When, let's say, you are doing 2 plus 4. It's the same 2, that's fine, but I need to go 4 units to the right. So 1, 2, 3, 4, and this is what you get, which is 6, and which is correct if it is unsigned. If it is unsigned, the number is supposed to be 6. 2 plus 4, 6. Makes sense. But what if the number you are dealing with is signed? Then the result that you are getting is -2. 2 plus 4 is -2, which is horribly wrong. And you can see there is an abrupt discontinuity here at this point. Whenever your computation crosses this point, things go catastrophically wrong. So 3 plus 1 is -4 in signed number system using 3 bits. And that makes sense because what you can represent is between -4 and 3 using 3 bits. Signed. Unsigned, 0 to 7. So whenever there is a crossing here, whenever it crosses here, you have the result catastrophically. And this is called overflow. Overflow happens only when you are adding 2 numbers of the same sign. And here it happened because you are adding a positive number, you are adding another positive number. So you get a number which is too big a positive number to be accommodated in the given number of bits. So it wraps around to the extreme negative value. And that's what happens here. 3 plus 1 minus 4, which is the other extreme. So this is overflow. So when will it be wrong, or when will the computation be wrong for unsigned numbers? When you cross here. So 7, 1, 1, 1 plus 1, 0, 0, 0. And there is a carry. So the result wraps around from the highest suddenly to the lowest, the other extreme, when it crosses this point, and that's carry.
So overflow is only for sign.
So overflow is meaningful only for signed numbers. Carry is meaningful only for unsigned numbers. And carry and overflow are like North Pole and South Pole, right? So they don't really have any connection with each other. And that's a very, very important point which a lot of people refuse to believe. They are almost diametrically opposite. Yeah. So yeah, overflow happens only when you are adding 2 numbers of the same sign. Overflow is only for sign numbers. That's why I am talking about sign in the first place. You add a positive, you add a, okay. You have a positive, A is positive, B is positive, and the sum is negative. Then there is an overflow. Or you are adding 2 negative numbers and you are getting a positive number. Then it's an overflow. The number is supposed to be very negative, but the magnitude is too big to be accommodated within the given number of bits. So it wraps around and goes to the other extreme, which is being positive. Okay? So now you have an overflow, but this is in addition. How about in subtraction? This is when you do A plus B. When you do A minus B, well, the story is a bit different, but well, the idea sort of remains the same. You subtract a negative number from a positive number, and you get a negative number. So plus, minus, minus should be a big plus, right? But if it becomes minus, you have a problem. Or if you are subtracting a positive number from a negative number, it's supposed to be very negative. but if it happens to be positive, we have it. Yeah. So in addition, overflow happens only when you are adding two numbers of the same sign, and if the result has a different sign. In subtraction, the two should have different signs, and the result should have a sign which is different from that of the first operand, or the first number. But one similarity that you can see is the result and the first operand should have different signs for overflow, whether it's subtraction or addition. For addition, the two operands should have the same sign. For subtraction, they should have different signs. So now we can combine all these and say, in addition, A31 XOR S31 should be true. In subtraction 2, A31 XOR S31 should be true, because the first operand and the result should have different signs. So you can identify that using XOR logic. What is the additional condition? For addition, A31 XOR B31 should also be true. Sorry, it should have the same sign. So it's XNOR. Because if A31 and B31 have the same sign, their XNOR will be 1. Their XOR will be 0. XNOR will be 1. Whereas here, they should have different signs, which means A31 XOR B31 should be true. So this condition is the same for addition and subtraction. And this is different. Now for addition, ALU control bit number 0 should not be true, because 0, 0 is addition, right? Whereas for subtraction, ALU control bit number 0 should be true. So now let's combine all these. You can see the common factor is A31 XOR S31. And now it is ALU control 0 bar A31 XOR B31 the whole bar, or A31 XOR B31 and ALU control 0. Now this expression itself is an XNOR expression. Something like, let's say, X bar, Y bar, or XY, which is X XOR Y the whole bar, XNOR. And so it is ALU control XOR A31 XOR B31 the whole bar. Basically, this is treated as one unit and then double, but eventually it doesn't matter. So you get an XNOR expression here and with this XOR expression. Okay, so the same thing here. And that is exactly what you have here. So S31 XOR A31 and the XNOR of A31, B31 and ALU control 0. So that is your overflow. Yeah. Same what we have. XNOR of all the three and XOR of the first operand and the result. Okay, so that completes ALU flags. The next one is comparison for equality. do you really need this in your ARM ALU? Do you have a scenario where you are checking if A is equal to B? Answer is not really. You don't do it directly. You only do A minus B and check whether the result is 0. So comparison is done using subtraction in ARM. Okay, whereas in other architectures like RISC-V, there is an explicit comparison. There are instructions which do comparison without subtraction. And then, how can you do it? You have to check whether all the bits are the same individually. And they all have to be the same for your eventual comparison to say, yes, they are the same. And how do you check that? You do an XNOR. If A3 and B3 are the same, this will be 1. If A3 and B3 are different, it will be 0. Opposite of XOR, right? By this time we are pretty familiar with XOR versus XNOR, right? So yeah. So all these have to be 1. That means all the bits of A have to individually match with the corresponding bits of B. And then if all of them match, we can say it's equal. So this is a direct comparison circuitry for equality. Okay, which is required for some processes like RISC-V. But even within ARM, there are scenarios where such a comparison is useful. Not inside ALU, but elsewhere. Like for example, we will see soon, pipeline hazard detection and appropriate circuitry to deal with it. That will require check of equality. Okay, to check whether the destination of one instruction is the same as source of some other instruction which is still in the pipeline. Okay, when we will get to pipeline, we will see. Then there is branch prediction, where we make guesses regarding whether the branch will be taken or not, even before the outcome of branch is available. So we guess, speculate. And we will see circuitry for that again in chapter 7, where we will require equality hardware. Okay, and if all you care about is to check whether two numbers are the same, you don't really need to do subtraction. Actually, a subtractor is a costlier operation, or subtraction is a costly operation than this. Here, to compare two 32-bit numbers, you require 32 XOR gates, which will all operate in parallel. So you don't have any sequentiality or cascading involved. But then you require a 32-bit AND gate to combine now, which is big but can't help it. But no matter how you implement it, it's still going to be a lot simpler than doing subtraction. That's my point. Yeah? But ARM does CMP using subtraction simply because, well, the subtractor hardware is available in ALU anyway. But these kind of stuff are supposed to operate in parallel with ALU. So you require equality hardware which is dedicated to this. Okay, so that completes comparator. The next one is shifter. We saw the use of shifter, right? We had incorporated shifter into our hardware, into our single cycle processor. But that shifter has to do shifting combinationally. And that's a shifter we are going to look at now. There can also be shifters which do shifting sequentially, which can be implemented quite easily and in a very hardware efficient manner using shift registers. Heard of shift registers before? You can have a bunch of flip-flops where the bits go from one flip-flop to the next, and you shift as many times as the shift specified or required to be done. Like for example, you can have flip-flops like this. And if you are supposed to shift this 4-bit value right by 2 positions, just give 2 clocks. Okay, then whatever you had here will end up here. Whatever you had here will end up here. And whatever you had here and here will get thrown away. Okay, and you have values coming in here, which will be zeros if you are doing a logical shift right, which will be the same as MSB duplicated, but that will require additional hardware if it is arithmetic shift right. but this is logical shift right, which requires nothing more than 4 flip-flops for a 4-bit scenario. Okay, this is the simplest possible shifting, but it will require multiple cycles to accomplish the shift that you want. Multiple and actually variable number of cycles. If you are shifting it right by 31 times, you require 31 clock cycles. Okay, which doesn't sound very appealing, right? So many processors do have so-called barrel shifters, which can shift by an arbitrary amount in a single cycle, that is combinationally, without requiring any clock. And that's what we are going to look at. By the way, having said that, a lot of simpler, cheaper hardware do not have barrel shifter circuitry. So there is no easy mechanism to shift by an arbitrary amount in a single cycle. Like if I believe some of those cheaper PIC variants which are used in embedded systems, I think do not have barrel shifters. Yeah, so whenever there is a shift, well, it will take multiple cycles, so slow. Yeah, so let's look at barrel shifters. So no clock involved, you give input and you get output within the same cycle without waiting for a clock. So here we are looking at not a 32-bit shift circuitry, a 4-bit shift circuitry. So you have a 4-bit value which is shifted by an arbitrary amount, and meaningful arbitrary amounts are 0 to 3. Because if you shift a 4-bit value by anything more than 3, you end up with nothing, right? So it's a 3-bit value, that's why shift amount just needs to be between 0 and 3, so 2-bit value. And for 32-bit case, the shift amount is 5 bits. The values to be shifted as well as the shifted output are 32 bits. 5 bits is good enough to specify between 0 and 31, which is a meaningful range for 32-bit numbers. Whereas here it's 4-bit numbers, so meaningful range is 0 to 3, so 2 bits. Okay, so let's see how we can implement a shifter circuitry. So you give shift amount as the control input to 4 4-to-1 multiplexers. Each is a 1-bit 4-to-1 multiplexer. 1 bit, here it's 1 bit, not 32 bits. Yeah, just 1 bit. And you require 4 such multiplexers to implement a shift for a 4-bit value. And let's for now assume that we are doing right shift. Okay, logical shift right, LSR. By the way, shift instructions even in RISC-V is optional. It's not a mandatory instruction. Yeah, so I think I don't remember exactly, but anyway, back here we have shift amount, which is a 2-bit value given here, and the wiring is done in such a way that you will get the correct result. So let's say if the shift amount specified is 0, 0. So whatever you give here, 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 and here are your outputs. And your output will now be what is given here? A3. So A3, A2, A1, A0, which is basically the unshifted version. Yeah. Now, what if you give 0, 1 here? SHINT shift amount is 0, 1. Then what we select is this, 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 this. And what do we expect at the output? Shifted right by 1. So it should be 0, A3, A2, A1. That is shifted right by 1 position, right? So simple. You wire it, hardwire it 0 here, wire this to A3, this to A2, and this to A1. Now you get the idea, right? Now what if you want shift right by 2 positions? Well, you expect 0, 0, A3, A2. Okay, so corresponding to the input control input 2. You give 0, 0, and now this is connected to A3 and this is connected to A2. That's ideal. So this can accomplish a shift right by an amount between 0 and 3. What if you want a rotation? Instead of LSR, let's try and do ROR. What will the changes be? Well, the connections for 0, 0 will remain the same. That's irrespective of shift, right? Because output is same as input. Now, if it is rotate right by one position, this is supposed to be A0, this is supposed to be A3, this is supposed to be A2, and this is supposed to be A1. A rotate right is a circular shift. It's kind of like shifting right, but the leftmost positions will be filled up by the ones which are pushed out to the right. So the connection for this is the same. This, now we are looking at 0, 1. These three have the same connections. So the 0, 1 connection of this multiplexer, this multiplexer, this multiplexer is the same. The difference is for this multiplexer. It was wired to 0 for shift right, but for rotate right, this should be wired to A0. That's the difference. Okay, and so on. You get the idea, right? Now, for a 32-bit shift, how much hardware do we need? You require 4 4-to-1 multiplexers for a 4-bit case. So for a 32-bit case, well, no prices for the same. You require 32 to 1 multiplexers. Is it a lot of hardware? Now, since getting an idea of how much hardware is required is becoming a bit difficult, let's quantify it in terms of 2-to-1 multiplexers. How many 2-to-1 multiplexers are required to implement a 32-to-1 multiplexer? Anyone? Okay, how will a 32-to-1 multiplexer look like? You have something like inputs I0 to, let's say, I31, and you will have 5 select bits, let's say S4 to S0, and you have still one bit output, 32-to-1 multiplexer. How can you implement it using just a 2-to-1 multiplexer, which we are fairly familiar with? So you have a select, you have input 0, you have input 1, and an output. So how many such multiplexers are required to implement this? That's a question. Anyone? The answer is 31. Yeah. How did that 31 come into picture? Yeah. You need to have one level of multiplexing like this, 8 of them, which can all be selected using the same bit, which is the most significant bit. So least significant bit, not most significant. So let's say this is S0. You give S0 here. So it will be I0 or I1 here, depending on S0. So if this bit is 0, then you will have I0 selected, here I2 selected, etc. Then you require 4 at the next level. Sorry, here, sorry, not 8, here 16. So you require 16, and here you require 8, the next level of multiplexing, and here you will require 4, here 2, and then one final multiplexer which uses S4, the most significant bit. The most significant bit will select between this half, upper half and lower half. And then, subsequent lower significant bits will do selection at various stages. And this is the one which selects between even numbered inputs and odd numbered inputs. So there are 16 even numbered inputs, 16 odd numbered inputs, right? Like I0, I2, I4, etc. are all selected by bit S0 of the select input. So you have 16 plus 8, 24 plus, or 28 plus 2, 30, plus one final one, 31. So now, how many 2-to-1 multiplexers are required in total here? It is 32 into 31 2-to-1 boxes. And that's about 1,000 2-to-1 boxes. Which certainly sounds a bit too much, and it indeed is too much. So let's try and see whether there are simpler or less complicated or less or more efficient hardware. What we do here is, use the kind of logic that we just had and use it to a higher level. So here you give the original input. Here you give the input that is shifted right by 16 positions. How do you shift it right by 16 positions? Do you really require a shifter? If we did, then we are again going back to the same point, right? No, shifting it by a fixed number of bits doesn't require a shifter. It just requires appropriate wiring. So how can you implement a circuit which shifts right by 16 positions? A 32-bit number. Give all zeros, and let's say if this output is, let's say Z. So Z31 down to Z16 will be all zeros. Z15 will be the input, let's say I31. If I is the input and Z is output. Okay, and so on and so forth. So finally you will have Z0, which is I16. Now we are already shifting it right by 16 positions, fixed 16 positions. And now we have an unshifted version and a shifted version. And you select between the two using the most significant bit of the shift amount. So the output here, output of the multiplexer here is either an unshifted version or a version shifted right by 16 positions. And this output now is connected directly to the next multiplexer input. And this output is shifted right by 8 positions. Again, it can be just accomplished by appropriate wiring. Okay, to input 1. And the distinction between these two is done using the next most significant bit, which is bit 3. Bit 4 is the most significant bit, next bit 3, next bit 2, bit 1, bit 0. Now you get the picture, right? And this is shifted by 4, shifted by 2, shifted by 1. Now let's see whether it makes a difference or is it identical to the previous case. Here, each multiplexer that we are talking about is a 32-bit 2-to-1 multiplexer, which is effectively 32 2-to-1 multiplexers in parallel with the same select input. Yeah, so this is basically 32 2-to-1 multiplexers. So here you have, let's say, A31, here it's like B31, and here it's A0, B0, and this is your output. Let's say Z31 all the way to Z0. So you are looking at 32 2-to-1 multiplexers, which is what we call a 32-bit 2-to-1 multiplexer. So it selects between two possibilities, but each possibility is 32 bit. Okay, so you are looking at 32 2-to-1 multiplexer per level, and you have 5 such levels. So how many 2-to-1 multiplexer equivalent do we have? 5 into 32, which is 160. So you accomplish the same thing with 160 here, whereas using this crude logic, you required about 1000. 32 into 31, which is 990. Okay, whatever. It's around 1000. Yeah. Okay, so this is a lot more efficient. Now, your processor has to support 4 different types of shift, right? Again, you could have these separate shifter circuits for each of the shift. There are 4 types of shift. And then you can have a 4-to-1 multiplexer, a 32-bit 4-to-1 multiplexer, where the selection is done using the shift type. Again, there are inefficiencies because some of the shifts can share a lot of hardware. Whereas here, I am assuming that I have 4 separate blocks to do each type of shift. And I just select the output based on the shift type that I want. That is specified in the instruction. Yep. Okay, and as you can expect, all those right ones can share a significant amount of hardware. They differ only in what is used to fill up those positions which are left behind after shifting. Okay, LSL is of course radically different. So my point is that yes, the hardware can be made more efficient by combining some of these, but for now we will just leave it at that. Next, multiplication. Now I forgot to mention something about addition. It's not there in the slide, but I have just wrote as a note for me. But if you want, I can just incorporate it into the slide. But the point is, since addition is such a commonly used operation, it certainly helps to have programmable hardware like FPGA have some dedicated support for addition. Rather than making an order out of very general purpose fabric, it helps to have some acceleration for addition, right? And indeed, modern FPGAs do have some dedicated hardware for addition. Or to be specific, to do carry look ahead. Modern FPGAs like Xilinx 7 series FPGAs do have 4-bit carry look ahead units. And to interconnect the logic that deals with separate bits, there is a high-speed network dedicated for that, so that you don't have to use any general purpose fabric. And this whole thing together is called a carry chain. Okay, it's essentially a carry look ahead unit with some dedicated wiring to deal with carries. It's called carry chain. If you are interested, you can read up more. But yeah, it's good enough to know that there are these so-called carry chains within configurable logic blocks. 4 bits. But even newer versions of Xilinx FPGAs, like Ultra Scale series, they have 8-bit carry look ahead units. Okay, so how do you make use of it? Well, the good news is just write A plus B. Okay, and the tool is smart enough to figure out that you are doing addition, and it is smart enough to figure out that if that addition has to be done fast, it helps to make use of the carry chain that is built into configurable logic blocks. But if you want a full control, if you are a control freak, nothing stops you from instantiating the so-called carry for component directly in your design. So you can use carry for just like other modules that you have created in HDL. Just that you don't have to implement carry code. It's already there in hardware for you. You can just assume that it's there and just use it. Okay? You don't have to search for an HDL code. There isn't. So it's a primitive. It's implemented in hardware. But the tool is smart enough to know that, well, you are looking for it directly. So it will just use it. So which one is better? Writing a plus sign or explicitly using this carry chain? Using explicitly is called instantiation. Whereas just writing a plus sign and making the synthesis tool do the job or figuring out whether to use it or not is called inference. Which one is recommended? Yeah, using plus sign is better because nowadays synthesis tools are smart enough to know that it has to use carry chain if it wants it to be fast, but it allows your code to be more portable, more versatile. It's not tied to a particular FPGA family, whereas carry forward is a feature of a certain FPGA family. So if you want to move it to, let's say, an ASIC or an Intel FPGA, well, you have a problem because that synthesis tool will not recognize carry forward as a primitive because that particular platform doesn't have it and is not by that. Yeah? So wherever possible, it's recommended to use inference rather than instantiation. But yeah, instantiation has its advantages, especially if you want to fine-tune things at a very low level, which rarely happens, but if you want to, you can. Okay, now multiplier. The reason why I just remembered that I had to go back and mention this is because modern FPGAs do have multiplier elements as well. There are these so-called DSP48E logic blocks, which are not conventional logic blocks. They are specialized for multiply and accumulate kind of operations. So they can do 25 by 18 multiplication and a 48-bit accumulation. So you can do like some plus equals A into B, where A can be up to 25 bits, B can be up to 18 bits. So it's multiply accumulate. And they are called DSP units because, well, I have mentioned before, one classic application scenario where you need to do something like this, which is something like sigma AI xi, is digital signal processing. To create digital filters or to do digital filtering, fast Fourier transforms, etc. All of them are multiply accumulate. And lately, in the past 5 to 10 years, they are more used for machine learning than for DSP, because machine learning also follows mostly this pattern, multiplying one vector by another vector, which again can quite naturally be done using these DSP 48 units. This again can be used either by instantiation or inference. So if you do something like A into B, if the synthesis tool decides that it's a good idea to use DSP units, it will. Basically, if it has DSP units left, it will use it. Yeah? So, in that sense, you don't really need to implement your own multiplier when you are doing FPGA designs, especially if you have enough DSP units which are unused in that particular design. But yeah, it still certainly helps to know how a multiplier is designed, because you might not be implementing your processor on FPGA all the time. If you end up in Intel or AMD, they are not going to take an FPGA and implement it except for prototyping. So yeah, we need to know how multipliers work. And one way you can do multiplication is exactly the same way you do pen and paper multiplication. You have partial products, and then they are shifted and added. So how do you do 230 into 42? You first do this, you get 460. then you do this, and the result is shifted left by one position, and then they are added up. So those partial products are summed up together. And they are shifted to respect the fact that when you multiply by 4, you are in fact multiplying by 40, not by 4. Okay? One radix is implicit, one radix position. So if it is one more here, then it's actually into 100. That is into radix, and here the radix is 10 because this example is decimal. Same thing in binary. Okay, except that things are slightly easier because you are either multiplying by 0 or multiplying by 1 to get partial products. And multiplying by 0 is basically using 0. Multiplying by 1 is using the multiplicand directly. Yeah? When you do A into B, A is what we call the multiplicand, B is the multiplier, and whatever you get here is the product. Right? So let's say you are doing this. First, you multiply here, which is basically the same thing as such. Whenever there are ones, you have the same thing, but with appropriate shifts depending on the bit position of the multiplier that you are using. And here, it's multiplication by 0, so it's just a matter of adding 0. And then sum up all the partial products, and you get your result. And this is exactly what an array-based multiplier or a combinational multiplier does. So there is nothing sequential here, so you have a huge array of orders. So here it's a 4-bit by 4-bit, so you are essentially looking at 12 full orders. In general, if you are multiplying m bit by n bit, you are looking at the order of m into n full orders. It's slightly smaller than m into n, but it's in the order of m into n. If you have m bit by n bit. So you can see the number of orders required is quite huge. So it's very hardware intensive. And the delay is also pretty high because you have seen that 32-bit addition itself causes a lot of delay. Now this is more than 32-bit because one level itself is 32-bit. And there are possibly like 32 such levels. It's actually 32 minus 1. So you can see it has to go this way and this way. So the delay is of the order of m plus n bits. For it to propagate all the way here and then here. Okay, so m plus n order. Now, how exactly does the circuit work? This is what you want to do. The least significant bit is simply A0 and B0. Multiplication is, in this case, for 2 bits, just an AND operation. So 1 bit, it's just an AND operation. And how about here? This plus this. So A1 B0 plus, it's not OR, it's plus A0 B1. And so on and so forth. So you can see, for each bit by each bit, you can do the partial multiplication using an AND gate. And then you need to sum it up all together. Okay? And you can go through the circuit. It makes perfect sense. So yeah, here is a 4-bit by 4-bit multiplier. Now, again, if you are creating a toy for your kid, this is probably too much money to spend. Because the kid will throw away within a day or two anyway, right? So, is there a more hardware efficient way to do things? You can do it sequentially. Okay, so I will talk about how to do sequential multiplication in the next class, but it's very, very straightforward to understand if you just go through. Okay, this is slightly trickier, but again, not rocket science. You can still understand within 10 minutes or 5 minutes. And then division, which is more complicated, And for most processes, division is the most complicated operation. And then we will look at how to accommodate signs, and then we will look at how to accommodate numbers which are not integers. And there are two techniques, fixed point and floating point, and we will see how those operations are performed. Okay, not too much at a hardware level, but once you reach this point, implementing it at hardware level is fairly straightforward as long as you know the algorithm. So the rest of it will be at algorithm level. Now, next week we have quiz between 7:15 and 7:30. So be here at around at least by 7, so that you can look at your seating order. I will publish a seating arrangement. Sorry? It covers the first 3 chapters. No, this is 4. Chapter 4. Chapter 3 is single cycle processor design. Now, before the actual quiz, I will do a mock quiz, which is through a poll, poll EV based, so that you will get prepared to this. It's open book, but you cannot refer to electronic devices. You can take notes on electronic devices, because we have no way to know whether you are using it to communicate or not. And the level of invigilation here won't be as good as a final exam. It's just a lecture quiz. So the only way I can ensure a fair play is to ban all electronic devices. You can refer to anything in hard copy, whether written or printed or whatever. I know it's probably not very environmentally friendly, but that's a price we have to pay for fairness.
Thank you.